With great pleasure, I welcome Dr. John Philip, our resource person for the talk.
Thank you, Aishwarya. So, what I'm going to discuss today is about smart or intelligent materials and their applications. But before I start talking about smart or intelligent materials, these are relatively new as compared to our traditional materials. Let me ask you a few questions, and obviously, I will not be able to have answers because we are on webinar mode. But at least I want you to think and answer to my question to yourself. The first question is that probably all of you must have born after 2000. So when you are a young kid or student, you would have seen CRT-based TVs. And now you see high-definition TVs, which are based on organic light-emitting diodes. You also would have seen computers, change in computers, their core as well as performance. This is what it is depicted here, starting from 1976 to 2009 and today. You see a lot of changes. Probably the computer dimensions would not have changed so much. But if you look at the performance of the computer has increased almost 2,000 times faster than the one which is made in 1985. This change you have seen. You have also seen that these dimensions of electronic gadgets in general, and if you look at this mobile phone, the early one that you saw during your childhood and the one that you have today are quite different. They're extremely powerful devices, and your smartphones can perform almost everything a computer or laptop can do it. So why this change is happening? I'm sure many of you must be knowing the answer to this question. Things are changing in the case of computer or mobile or electronic, intelligent electronic devices, mainly because the fabrication, semiconductor fabrication technology has changed since 1970. So what you see here is the first point contact transistor, which was built in 1947. It is a single transistor is what you see here. But now, let me put the laser point. Yeah. So what you see here is single point transistor. Now, the processor that you see here on the right side has 1.9 billion transistors in a square inch area. So this is the reason why the power of computer and many other gadgets or devices are shrinking. It is the process as well as the materials. Of course, if you talk about semiconductor technology came in 70s. Okay, the process was learned a little bit early. But you see, the first fabrication was done in 1971. So the process was about 10 micron, which is little smaller than the diameter of a human hair. So at that time, obviously computers were not very powerful. The devices were not powerful. And that is the reason why the size of the gadgets were bulky. Now where you stand somewhere at 5 nanometer technology in 2020, 5 nanometer from 10 micron down to 5 micron technology you have. That is the reason why you are able to see the changes in computer technology. And obviously you would have studied this in electronics. Moore's law, which says that every 18 months, the number of transistor functions in a square inch of silicon is doubled. That is what we have been seeing all along. This applies to processor, memory chips, and interface functions. And your smartphone today has over 1,000 times this clock speed and over 100,000 times the memory size of the first IBM PC built in 1980. So all these things, all these technologies that you see today is because of materials. This is the point I want to emphasize. Materials are the key ingredients to any technology. And materials unite applications in all disciplines. Why we didn't have all these technologies before? We didn't have materials to manufacture these things. Of course, the silicon wafer that is used in ICs or chips, the process of making silicon wafer was invented in 1950s. So before that, it was valve technology and technologies were different. So the technologies are coming because of the materials that we invent. Okay, now for the students, I have a question. Are you happy with the current technologies? Let us take two examples, the laptop and mobile phones. Are you happy? If it was an auditorium, I would have heard answers from you, but this time I cannot. But what is your answer? Are you happy? Of course, this boy is quite happy because, whatever he wants, he can do it with the laptop. And this young girl is also quite happy because her requirement is, minimal. And she needs to talk to her papa or mommy, okay? And then she will leave the phone there. And this boy may be playing some games or watching a movie, and he will put the laptop down, and he doesn't sit with it for a full day, and he doesn't do games, and he doesn't do any computing work. But is it the case with you people? Of course, these are the situations you can see in reality. The biggest problem with laptop or mobile today is the battery. Of course, there are improvements over the years, but still it is a problem. It drains very fast. What you want is longer battery life. And of course, these mobile phones or laptops will have to work in harsh conditions. I've given a few examples. All these conditions it has to work. And many of these students are addict now. We have to send WhatsApp or messages even when you eat or drink or taking shower. So this case also, the phone should not go bad. And of course, the laptops, if you use it for longer time, it generates a lot of heat. So what you see here is the thermal image of a laptop after an hour of use. You can see the red area, the temperature is quite high. And this is one problem that we have been facing. And obviously, the latest laptops may not be generating this much heat, but still it is generating heat. What happens when it generates heat? Heat is produced from the electricity, it is the power which is consumed by the laptop. So the power is wasted in the form of heat. That is what it is happening. So of course, if you use it for longer hours, you can even make a bullseye. That's the kind of temperature a laptop is generating after half an hour of use or more. And this situation has to change. Okay. So what are the requirements? Instead of me getting answer from you. I have listed the requirements. We need longer battery life. Ideally, we need all day long battery. And we need even faster processors. We have problems. And we need our devices to generate less amount of heat. And we need better keyboards, touch screen. And in future, we may not be using the keyboards, mouse, and other things because it is going to be controlled by eye or gesture. Now we have Siri, Alexa, you can talk and get what you want from your computer or mobile phone. These technologies are going to take the front stage, and we may replace all the keyboards and touch screens and other things. You will be able to speak, or with your gesture you can control your computer, and artificial intelligence is also going to be taking a major role in the coming years. Another most important thing is, the flexible and thinner devices, flexible electronics. You may be able to fold your laptop or mobile phone and put it in the wallet. This is the kind of electronics being developed today. Now, see, we are talking about all day battery. And, till recently, I thought it is going to take some time. But last month, you would have seen this news from IBM. World's first 2 nanometer chip technology is unveiled by IBM on May 6, 2021. 2 nanometer technology, because initially what is thought by experts is we may not be able to go below 5 nanometers. But you have 2 nanometer technologies demonstrated, and we can achieve 45% higher performance using this technology. But obviously, this is a demonstration. Once this kind of chips are made, what is going to happen is that 75% lower energy is only required with respect to the 7 nanometer or 5 nanometer technology. So you will have to charge your cell phone only once in 4 days, probably 2 or 3 years from now. And in other countries, anyway, India, it is not a big issue driving, and we have drivers, and it is not very expensive. But in foreign countries, abroad, you will be able to see autonomous vehicle with the self-driving cars. This is what it is going to see. And also, we slash the carbon footprint of data centers because, the existing devices generating a lot of carbon, and this can be contained if we use 2 nanometer technologies. So I conclude this first part. Why materials are important, why we are talking about new materials, why we are talking about intelligent materials, why we are talking about smart materials. The reason is that, we have all kinds of materials today, but of course we want improvement. I have talked about computer, mobile phones and all. We still want powerful, and we need to get rid of some of the problems that we have today. Similarly, we need materials in all these domains. That is what it is listed. If it is light emitting diode, if we have better materials, it can be operated with less power. And the efficiency of this light emitting diode, if we can improve, there will be huge saving on power. Similarly, high-speed communication, we are talking about 5G, 7G and all. So we need better materials for that. Obviously, we have all kinds of material, but we want to improve it further. And we also need high-strength and lightweight materials. I'm going to show you some examples in my lecture, how we can produce high-strength and lightweight materials for aircraft and rockets, and also for other applications. And we also need high temperature ceramic materials for jet engine and corrosion resistant material. I'm going to show you some examples for such material developed in laboratories. So in our search for better materials, we came across a class of materials with ultra fine dimensions exhibiting interesting properties. These kind of materials called nanomaterials or nanostructures. Of course, you must be familiar. I can give a talk for 2 hours or 3 hours on nanomaterials. It is not possible for me to cover nanomaterials in this lecture. So I just show you 1 or 2 slides on nanomaterials and nanotechnology, because most of the students are graduates. The very basic things you need to know about nano, the definition, I will show in the next slide. So this is what you need to know all about nanomaterials. Nanomaterials exist in nature in different forms for centuries, but nano has become popular only since 2000 or so. So what is nanomaterials? Materials with the dimensions in the range of 1 to 100 nanometer, which is called nanoscale, is called nanomaterials. So the materials with the dimension above 100 nanometer comes under traditional materials, that is called bulk material or normal materials. And the materials with dimension below 100 nanometer up to 1 nanometer comes under the category of nanomaterials. And what happens? A question to the student: what happens if the dimension is less than 1 nanometer? Of course, that is the kind of materials you study in atomic molecular physics and nuclear physics. You talk about material and dimensions smaller than 1 nanometer. So the nano is an interface between sub nanometer or atomic and nuclear physics and the material science. And nanoscience is the science of matter. Any science that you do with nanomaterials is called nanoscience. And nanotechnology is the design and production of structures or devices or systems by controlled manipulation of materials at nanoscale. In a simple way, you have seen the nano fabrication, the ICs and chips you have seen. That is a process. Now the process is called nanotechnology, because the feature size, the transistors, interconnects, everything is in nanoscale. And you remember my earlier slide, the smallest size that we have in our device is 5 nanometer 5 or 7 nanometer technology. And what you are going to see 2 years from now is going to be 2 nanometer technology. And obviously, we don't know what will happen if you reach that and below. And there is a limit. There are problems. Anything you take and keep, it will not remain there. The thermal energy, the room temperature is good enough to, everything will be flying off and, melting it at room temperature. The size is extremely small. So, second thing you need to know, these are the definition you should know. And second thing you need to know is that the nanomaterials are different from bulk material in terms of their physical and chemical properties. One fine example is that if you take gold, you see the color of gold. And if you take nano gold, the color will not be the same. The color can be different. It can be black, brown, or yellow, or red, or violet. The color or the properties of materials depends on the size of these materials. So nanomaterials exhibits very interesting properties, and a physicist, and this is physics graduates and physicists can be proud of. Richard Feynman, he was a famous physicist at Caltech. He is the person who inspired or who talked about nanotechnology in 1959. That is much before the nanotechnology or the nanotechnology term was coined. And in 59, He talked about miniaturization. He asked a question to the audience. Why can't we write the entire 24 volume of Encyclopedia Britannica on a single head of a pin? Imagine in 1959, we didn't have the Pentium chips or the silicon wafers based devices were not there. So nobody knew what is possible. But the person, he knew physics. He said the principle of physics, as far as I know, cannot violate any rules if you reduce the size to nano size. Okay, so many things he talked about were prophetic, and it is a reality today. Now you have pen drives where you can write the entire encyclopedia. So this has happened how many years later? 60 years or 40 years later, we have achieved what he has talked about. And one more thing you need to know about the nanoscale material, they exist in 3 different forms. Broadly, we can classify them in the form of thin film, in the form of nanotubes or nanowires, and in the form of nanoparticles. They're called 0-dimensional, 1-dimensional, 2-dimensional materials. There is a classification. Of course, I'm not going to discuss that today. But you tell, in the case of thin films, all the coatings that you do on materials, you can have a thin film of 1 nanometer or 100 nanometer coated on any substrates. That is the nanostructure in this case is only in one direction. Okay, that is the thickness. In the case of nanotubes, you have 2 directions, the nanostructures, 1 to 100 nanometer. So you have the diameter of the nanotubes or nanorods or nanowires in the second case, and in the third case, in all 3 directions, it is nano. That means the particles, nanoparticles, where the diameter of the particles are in nanoscale. So nano is extremely small. You cannot see with the naked eye. What you can see with the naked eye is the smallest thing you can see is probably the human hair, which is about 40 to 100 nanometer is the 100 micrometer is the dimension. So it is 20,000 or 50,000 times smaller than the human hair. And the light microscope, if you take, again there is a limit. Limitation comes from the wavelength of light which is used. So you can see something like, if you use a green or blue light, you can see something like 200 nanometer. That is the smallest thing you can see with the best microscope. And if you want to see real nanostructures, you need to use an electron microscope, which is quite complicated and expensive. That is why, when you work with the nanomaterials, you need to have very good facilities to. And to see the nanostructures, how many times magnification you need to put, I have one slide. This is what you see with your eyes, your hand. If you put a 10x magnification, you are expert in zooming in with your cameras. Okay, if you put a 10x magnification, you will be able to see this box magnified, and that's what you see. You put another 10x, you see that box magnified in this, your hand is no longer beautiful. This is the kind of structures and wrinkles that you see in your own hand. So what you see here is 100 micron. You have not reached a nano. You put 10 raised to 4 times the magnification. You put another 10x magnification. You will be able to see a white blood cell. You must have studied this in biology. It is 10 micron is the diameter of a white blood cell. If you put another 10 times magnification, you can see finer aspect of the white blood cell. And if you go to another 10x magnification, that is 10 raised to 7 times the magnification, you will be able to see 100 nanometers. The length is 100 nanometer. And what you see here is the helical structure of the DNA molecules. Okay. So it is not very clear, the helical structure. You have to put another 10x magnification. You can see now the helical structure. And if you put another 10x, you would be able to see the constituents of helical structures. So this is what you see, and this is the kind of magnification that you need to see nanostructures and nano features. So that's all about the nano part. So although nanomaterials and nanostructures are relatively new to us, they have been present in nature for millions of years in plants, animals, minerals. What is interesting about nanostructures or nanomaterial is that they exhibit very interesting properties. What are the interesting properties you can see? I just want to give you a few examples. The first one is, if you look at the seashells nacre, for example, it is made of calcium carbonate, but it is extremely hard. It is not easy to just break it like the chalk pieces that you use. The chalk pieces are also made of calcium carbonate, but this structure is very hard. That is essentially because of some nanostructures inside these bricks. I just show you a little later. And you also wonder how gecko is able to climb up and sit on the roof of your building. If you have curiosity, you would have thought about this. And it is able to move up and down without any problem. Sometimes it may fall, but in general, they can move up and down without any problem. Again, there is a nano features on the toes of this gecko. That is what it is making this gecko to move up and down on the walls or smooth surfaces. And you would have also seen, obviously you must have studied in optics, saw bubbles exhibit colors. What is it? There is a nano in it again. And of course, if you have finished your optics, you should be able to explain. And you also see the butterflies or the peacocks exhibiting beautiful colors. And these colors are not pigmented colors, not the colors you see on painted surfaces. In paint, if you take it, the color of the paint will be the same color as you see on the wall. But in this case, if you take the wing and you crush it, you will not see blue color. So it is called the structure. Nanostructures enable different colors. And this is what, again, another interesting aspect is that you all must have seen lotus leaves. During rainy season, it's very, very nice to see the water droplets bouncing off from the surface of lotus leaves. It bounces off. It is always dry. As soon as rain stops, it is dried. Whereas the other leaf, if you take, they are wet and the surfaces are wet. And you may wonder why it is remained as dry surface. So this is, I show a cartoon and you should have curiosity to know all these things. As a student, if you have curiosity, you learn more, you get better insight, you go deep. And nowadays it is quite easy for you to get all this kind of information and you become a better person or researcher or scientist. You can achieve these things if you have curiosity. And you must ask this kind of questions to yourself. If you have these questions, of course, you can ask questions to your teacher. You can ask questions to yourself and find answers from various sources, books, the net, and other authentic resources you will be able to answer. And I'm sure you have answers to some of my questions, but for the sake of completeness, I just explain this in a simple term. I don't have much time to discuss all, but this should have been a nano talk, then I would have. So this kind of shells are hard because you have a sort of structures the bricks, the calcium carbonates are like bricks. These bricks are arranged very nicely in a fashion, like the bricks are arranged. This is the reason why it is extremely hard. It is called a hierarchical structure. Of course, I'm not going to talk. Now, there are a lot of interest in this kind of materials, because if you can make this kind of materials in our lab, it is very, very useful, the high temperature ceramic material. And these materials, if you can make in lab, it can be stronger than steel and other material. But it will be maybe 1/4 of the weight of steel. So you can save a lot of, a lot of, it is strength wise, it is as good as steel or other metals, but the weight wise, it is much lighter, and it has a lot of application in aircraft industries, because aircraft or space industry, the payload, every kg you take up, you need to pay a huge amount of money for that. And the gecko, if you look at the toes of this gecko, the toe region, you can see nanostructured hairs. And these millions of foot hairs are able to create a very strong attractive forces between the surface and the toe of geckos. So again, a nano feature comes into picture. And now what the researchers are trying to do is to create that kind of toes with the millions of foot hairs, so that we can have wall climbing robots, and this can go and work in toxic environment, radioactive environment, high temperature environment. And one day, probably 10 years from now, people or you will be able to climb up and down using special gloves made of gecko-like technology, like a Superman. Right? So these are the things possible with the technology, with the nano materials and nanostructure. Now, the other question is lotus leaf, why it remains dry? It is called a self-cleaning. If a dirt is there, it is taken by the water, which is splashed on the surface. So it took us several centuries to understand, and nobody understood why the lotus leaf is having a self-cleaning ability. So in 1977, a German botanist decided to look at the surface of lotus leaf, and he has done it. He has taken and to a scanning electron microscope, which were popular at that point of time in 77. Imagine. 77. This has happened in 77. He published a paper showing this kind of structure. So what is seen here is you have micro bumps on the surface of lotus leaf. Of course, you cannot see with the eyes. The reason you know. And if you zoom in on of this bump, which is about 10 micron, you see this kind of fine pollen-like structure. These are the wax crystalloids on the surface. So this micro nanoscale surface roughness gives rise to the self-cleaning ability for this lotus leaf. And this property now can be utilized for controlling corrosion. See, this kind of situation you see, even your cycles or your motorbike, cars, railway bridges collapsing, ships are sinking. This is all because of corrosion. Corrosion is what? It is an electrochemical reaction. The water react with the surface, metal surface, and corrode it. It forms different oxides. And the amount of money which is spent is 3 to 4% of GDP. And this money you can save if you use lotus leaf-like technology. Because if you use lotus leaf-like technology, your gate or your vehicle will not wet the surface. So what I'm showing here is the structures which are created in our lab by our students. They both are Malayali students. Rasida, she's doing PhD, and Manoj finished his master's and is pursuing PhD abroad now, US. And what he has done is he has made a special coating on the surface, and which looks similar to what you have seen on the surface of lotus leaf. And you can see the droplets which are, which the droplets are not spreading on the surface. It remains like balls on the surface. Let us see a movie here. And this is the surface. One surface was coated, one surface was uncoated. And let us see, this is the uncoated surface. When you put droplets, you can see the droplets are there. And here you see the droplets are rolling off. So what you're seeing here is a surface which is similar to lotus leaf, which is called super hydrophobic surface. And now the self-cleaning action he has demonstrated here. And one surface is coated and this is uncoated surface. Okay, this is uncoated surface. To demonstrate the self-cleaning action, he has put some dirt on this, some powder particle. And this is the coated surface. There also he put some powder particle. He kept it slightly inclined position. Both substrates, both are I think SS or P91. It's a form of stainless steel. And now you see in this movie, what happens if you put water droplets? It is wetting the dirt on the surface and it remains there. And in this case, what happens? You see, the dirt particles are cleaned by water droplet. Exactly the way lotus leaf is keeping its surface clean. So this is the wonder. This is what you can learn from nature. You can do in your lab. It is not very, very expensive, or it is not very difficult thing. And you are going to see so many technologies in the coming years. This lotus effect started. People started working on it some 10 or 20 years back, and now a lot of progress is made, and we will be able to address corrosion, and you can make all the surfaces remain clean, and your fabrics or car or solar panel, all these technologies where this kind of surfaces are important. Now I move on to my last part, is smart, intelligent, or it is also called stimuli response. All of you must have seen this plant. What is it called? In Malayalam, we call it Totavadi, right? And what is special about Totavadi? The speciality about it, if you touch it, fold its leaves and droop inward. This is what it happened. Immediately it will close and then it reopens. This is the speciality. So in this case, what is happening is the plant, the leaf is able to sense the vibration or touching, the pressure, it is able to sense and it is able to act. And we have similar materials. For example, the piezoelectric materials and the shape memory alloys, you can see it. And you can see photochromatic glasses. Your glass, when you go outside, it becomes darker. But when you are indoors, it is again transparent. And you have polymer. This is familiar with the polymer chemist. And some solution becomes transparent and it becomes opaque or translucent when the temperature is changed. So in all these cases, including Totavadi, what you see is, if you touch it, that is a stimulus, we call it stimulus, touch or vibration. It is able to sense and it is able to act on it. So smart materials are, the definition, materials that can respond to a stimulus. Stimulus can be temperature, light, magnetic, electric field, and it will be able to change the conformation, transparency, or the size of the materials can be changed, or shape of the material, volume, viscosity or conductivity, all these properties, one of these properties could be changed. And today's talk is about two such materials. So the definition of a smart material, all of you must be knowing, because after sometimes somebody will ask what that John Philip has taught you and what are smart materials or intelligent materials. Ellarum idinte answer paranjirikkanam. Okay. So the smart materials are intelligent materials, are materials that can respond to a stimulus and change its functional properties in a significant manner. This is the definition. Because intelligent, we call it intelligent because it can remember the old shape. For example, you saw a movie where the surface was straight. When it is heated, it bends. And when you remove the heat, it is again back. If you use your photochromatic glasses, again, it is transparent when you are inside. If you go out, it is opaque. So that is the kind of material called smart material, intelligent material, or it is also called response stimuli material. I'm going to show you some video. So this is on material, it is a fluid, and if I keep it in an electromagnet and apply a magnetic field, you see the fluid from the bottom of this vial will be driven to the magnetic field area, that is the pole piece area. It can be driven, and if you remove the magnetic field, it's again a liquid. And what you see here is in the bottle, it is a liquid. I just tilted it to show that it is a liquid like water. But if you put a small toy magnet, you can invert this, and you see this liquid remains, and the fluid is able to hold its weight. And this is the natural color of the liquid. When you apply magnetic field, the color of the fluid is changing. It is not a single color. You can generate all colors in the fluid. And these fluids are made in our lab, and they are called magnetic nanofluids. I'm going to show you some movies on this in the next few slides. So what are these fluid? It looks like a black fluid. So what is there inside? Inside what you have is nanoparticles of iron oxides. So the red spots that you see here are nanomagnets of iron oxide. So you know that in magnetism, you must have studied ferrimagnetism, super paramagnetic may not be studied, but you paramagnetism. So these are fine, ultra fine nanomagnets suspended in a fluid. So you know that if you want to take bigger particles and try to put in water, immediately it will fall down. But if you make it smaller, like solid molecule, the Brownian energies or the thermal energy is good enough to keep the Brownian motion. So in a simple language, I can tell you that, so these particles, when the size is about few nanometers, they are like molecules. So if you have a powerful microscope to see water, water molecules, you can see the water molecule jiggling in the in the glass of water. The same kind of movement you will be able to see in this kind of fluid with the nanoparticle. So this fluid is made with the nanoparticles of iron oxide, and that's the movie I promised you. And this is a fluid which I'm holding it, and I just put a magnet here. When I put the magnet, what you see is I can invert the vial. I'm able to invert the vial. Fine. And it's like a solid. And when I remove the magnetic field, it is again a liquid. You see how I'm able to play with this fluid. It's wonderful. It is not magic. It is real. This is the power of nanoparticles. And now let us see how it works in an electromagnet. So this is field on, electromagnetic with field on. Now I just switch on the magnetic, switch off the magnetic field. I will switch off the magnetic field. When I switch off the magnetic field, slowly I can reduce. I cannot just put off. It's an electromagnet. So you see, the liquid is at the bottom. This is the magnetic fluid I am talking about. Now again, I will put on the magnetic field. You see, the fluid is driven to the place where you want. So this fluid has wonderful properties, and we have developed several interesting applications for this fluid in various fields. And this is the fluid I told you that it can change colors. Let us see. You see, the color of the fluid is changing. 4 bottles I have kept, and you can see one is orange, green, yellow. And then again, if I reduce the magnetic field, switched off the magnetic field. This is the natural color of the fluid. And when I apply magnetic field again, you would be able to see the color. It is a totally reversible process. Of course, this has again so many interesting applications. This is the first time a fluid like this is made in a lab. So initially I've done some work with a French collaborator, and in IGCAR, after joining as a young student, we have prepared this, and last 20 years we are working on this kind of fluids, and almost we have invented 5 or 6 or 7 very interesting applications. And you can also see how the transmittance is changing, and probably Reggie will talk about this. And you see the transmittance, if you'd like to try to send a light beam through such a fluid, a thin film of fluid, you can control the transmitted light intensity. Now, what exactly it happens when a magnetic field is applied to such a fluid? Of course, you can make slightly bigger particles around 200, 250 nanometers. So you can use a phase contrast optical microscope. And then you apply magnetic field and you can see the nanostructures formed under microscope. Let's see the action of this. So these are the nanostructures in the form of thin rods. And these nanostructures are completely dispersed in the water, in the fluid. And these are the nanostructures I'm referring to. And now how it is getting ordered, aligned, or it is changing its properties when a magnetic field is put on. So here we have a magnetic field. You can see all the particles are forming one-dimensional structures along the direction of the magnetic field. And then when you remove the magnetic field, these structures disappear from in the fluid. So what you have seen, you see the excitement. I was quite excited. I was working with a young student. And, when I see this kind of structure, I was very excited. I didn't know what to do. But then, after several years, we came up with a discovery, which is this one. We have demonstrated that this kind of fluids, the black fluids, can carry heat very effectively. So the concept of tunable thermal properties introduced by us in 2008 for the first time. And we have demonstrated that this kind of fluids are very, very useful for effectively removing heat from hot object and electronic device and gadgets. And Japanese people are using now this technology to effectively remove heat from supercomputers and other devices. All you need to do is to have a microfluidic channels on the device so that the fluid can carry the heat very effectively. And that's what it is shown here, 250% more than water. And the color changing property, again, we have used to image defects on material. So what is happening is, if you have to get your bonds, fractured bond or internal organ imaged, you have to go to X-ray, CT or MRA, or you can also do ultrasound scanning. Here, replacing all these technologies, see, if it is a ferromagnetic material, of course, it cannot be done on human, but if it is a ferromagnetic material, which is used in many devices, for example, the rail tracks are ferromagnetic, so you can inspect, instead of ultrasonic scanning, you can use this technology. And we have demonstrated in 2000 that this is a patent. And we have shown that the color changes can be manifested because of defects present. So in a layman's language, what I'm saying is, if a material has a defect, a crack with a thin film of this fluid, we will be able to find where the defect is present. In this case, you know that there is a defect on the back side, which you cannot see from the front. And there is another defect. It is a circular one you have seen before. And now you put a film of this fluid and apply magnetic field. You will be able to see the region where the defect is present. This is the rectangular slot and this is the cylindrical slot present. So even if it is inside, you will be able to manifest this. This is what it is demonstrated. And of course, the color change has also application in filters. You will be able to filter one particular wavelength from the light. And it has also application in sensing. For example, you go to hospital to measure the electrolyte or water, whether it is pure or it has contaminant. This can be, tested using this kind of magnetic fluids, where if it is contaminant water, so you will see a different color. So by looking at the color change, you can say this is safe, this water you can drink, this water is unsafe. That's the ultimate goal from our side. And the last part is that we are also working on cancer therapy. This kind of magnetic nanoparticle can be injected to the human tissues, the region where the cancer or tumor cells are there. And this is the advanced area of research, and it is already demonstrated that these particles can heat and ablate the cancerous cells, and that is what we are doing. And it can also be used for effectively delivering drug molecules to the lung cancer. For example, this is a work which is done. So I think with this I come to an end, and just I have few more slides and some advices to young students. So what I've shown here is the importance of materials in our technology. We started with the simple materials like metals, plastics, silicon, and we live in an era called materials age today with all kinds of material. And these materials have transformed our life. Now, we need better materials for solving many of our problems that we have today. As I told you, the improving the battery lifetime of your mobile. And similarly, we have requirements in almost all domains. And that is why we are working on new materials or better material or smart materials. Smart materials are materials that can change its properties with a stimulus. This can be electric applied field or light or other stimuli. Now, just I want to tell you a few stories to the young students. I think I have another 5 minutes. Rajesh?
Okay, sir.
Another
okay,
few.
Sir.
Okay.
You can take.
Yeah. So see, for example, physicist, I took this example for the physics student. Piezoelectric effect, all of you have studied. It is invented in 1880. Okay. So it is the ability of material to produce electric charge when it is stressed or otherwise versa. But, in 1880, it is discovered, but, no applications for almost 50 or 60 years or 100 years. Now, if you take piezoelectric effect, you see, this is a list of applications. Even if you go to the ultrasonic scanning, that is the piezoelectricity is the basic principle which is used. And in almost all domains, even the dot matrix print, ink printers, piezoelectric speakers, and cell phones, everywhere piezoelectricity is used. But of course, the material, better improved materials are produced over the years. So there will be a gap between the discovery of an effect or discovery of material and the technology. The technology will improve with the time as you have more and more technology. And the second advice to a young student is don't get distracted. Even if you are discouraged by your seniors or your peers or your faculty, you continue to invent and continue to think and produce. Take the example of Michael Faraday. Michael Faraday was a young fellow who demonstrated electricity for the first time. So our Prime Minister visited his lab and, he has demonstrated this to him. And this guy, William Gladstone, the British Chancellor, asked him a question. Yeah? Will it ever find any use? This is the kind of question a person, a Prime Minister, a Chancellor has asked to Michael Faraday. You see the polite reply of Michael Faraday. Why, sir? there is every possibility that you will soon be able to tax it. See, that's the vision of a scientist. And the last part, one slide, this is what I want to, the message I want to convey to all our young colleagues, because the future of our country is with you, the young students. 60% of our population is under 30 years old. You know, many of our, you, after your graduation, or your seniors, or your elders, or your relatives, or techies, you know, and scientists. You know, I was also abroad for 4-5 years, but I decided to come back and work in our country. But that is not the case with many youngsters today. We can see a lot of our people are migrating to, you know, Canada, USA, Australia, all these kind of countries. Why? This is a question I ask. You know, I, as a young student, when I visited France or Singapore or Germany or USA, I was, very happy to see all technologies in 90s, you know, ATM counters, all technologies are available here. But what is not available here is this kind of discipline and order. Any shop you go in Europe or other countries, you see people standing. Now we do that because of social distancing requirement. But if you go to a supermarket or a tobacco shop or newspaper shop, you can see in Europe all the people will be standing in a queue with 1 meter distance. That's the discipline. You see, the streets are cleaned and nobody is damaging. And how beautiful the cities are in various places, and you would have seen in movies. And discipline, traffic rules are followed. You see in Japan. Is it what it is happening in our country? No. See, this is why many people are interested in migrating to countries, because everything is fine and you don't, everything is clean. Everything is nice. People are behaving nicely. What is the problem with us? The problem is with us. We cannot talk about government or, your principal or HOD and other. We have to get disciplined by ourselves. Please aspire to be a good citizen of the country. And obviously, these are the things you need to do. Obey rules, traffic rules, so that our roads will be safe. Respect others. This is very, very important. Please do that. Be honest. Honesty is valued the highest. You may be the best student. You may be the rank holder. But if you are dishonest, you have no values. I can tell you this all. And maintain moral and ethical principle. And obviously, other things are also. And, you have a concern about others. As a young boy or as a young student group, when you travel in a bus or car or in flight, you may have a habit of making noise, but you have to see the adjacent old man. He may have a heart problem. He may have a problem. He may be coming after 16 hours of travel. He need a nap in the train or bus. And you shouldn't talk too much and, make others feel bad. So my advice to all the students, this is one reason why I give talk to young students. Please, and let us do that. And you don't think that, everybody is doing, nobody is following you. Everybody is spitting on the road. Everybody is putting rubbish on the road. I will also do it. So what is the difference? Please don't do that. You make a change. Maybe nobody is following. But when you do that, the other fellow will observe. He will observe, yeah, he is not putting anything. He is clearing everything and he is maintaining distance. And that fellow also may change. So this is what the advice I have to the young students. And I think Professor James told me to show you some of the facilities, and at some point you can visit. We have all kinds of characterization facilities, magnetic property, X-ray. This is the dynamic light scattering rheometer, phase contrast optical microscope. TGA, DSC, and this is the FTR system. These are all available in my own lab. I have established, and this is the optical microscopy where you can see this nanostructure, slightly bigger nanostructure can be imaged and controlled. And this is something called magnetorheology. You can control the magnetic field and see it. And this is the setup for cancer therapy. We can heat this sample and look at the temperature change which is happening, which can be used to treat cancer patients. And this is a homemade setup. It is a highly advanced force measurement setup which is made by me and a student, and a few students have completed this. And this is a unique tool to probe intermolecular forces between particles. And this is a inbuilt, home-built light scattering experimental facility, automated, fully automated. You can see all the control, which is made in my lab, and at least 3 PhD students have completed their work, and it's an incredible experiment set up to look at the structural transitions in nano systems, and these are some of the other facilities. So I come to an end. I think I'm precisely 1 hour for 10 minutes. And what I've talked about are materials. Materials are building blocks. And these building blocks, with proper thinking and imagination, if you put them together, you make this kind of toys using the building block. For that, remember the quote of Albert Einstein: imagination is more important than knowledge. Imagination encircle the whole world, whereas the knowledge has boundaries. If you have both, you can do wonderful things. I conclude my talk with a story from Rabindranath Tagore. It's the story of a sun and a candle. When the sun went down in the evening, he asked everyone on earth, who will take up my responsibility of providing light? No one replied. A candle in the log cabin answered, my lord, I cannot light up the whole universe as you do, but I will try my best to light up this small room. So, 2 messages. I've done the job of the candle. I'm not a great scientist. Okay, some of your faculty members and friends were very kind to tell good things about me. So I have limited knowledge in non-domain. That is what I tried to share to this small group. And we have great people with the knowledge like a sun. And the second message from this story is also very linked to what I told before. And we may think that, we cannot change this world. We cannot change this, these conditions. But you can do the bit. You can do the bit like the candle. Candle ചെയ്ത കൂട്ട് നിങ്ങൾക്ക് നിങ്ങളുടെ കാര്യം ചെറിയ ചെറിയ കാര്യങ്ങൾ ചെയ്യാം. So that will be, very useful for our country, and, become a developed nation in some years. So I conclude, and I once again thank the management and Professor James, my good friend Thomas Verghese, Dr. Rajesh Kumar, who spent a lot of time to set this problem, and Professor K.D. Thomas, principal, and Father Francis, and all these people for giving me this opportunity. Thank you very much.
We have just witnessed an insightful lecture by Dr. John Philip. It was highly motivating, inspiring, and informative to all of us. The session included the basic features, importance, applications, and the requirements of smart materials. I am sure that all of us are highly benefited by this talk, and as it will help us to mold our future research activities. On behalf of the management, principal, and all the participants gathered here, I express my sincere thanks to Dr. John Philip, sir.